Alright, just wanted to mention that some of you came after class mentioning that I forgot to write that numbers, those numbers. Alright? Okay, so the next is the derivative of a constant times a function. Well, that's just, the same general power rule multiplied by a number. So let's differentiate f of x, 5x to the fourth. So f prime will be, so the constant multiple we had for 5 times the derivative of x to the 4, which is 4x cubed, and all we do is simply multiply 5 times 4, which is 20x cubed. Alright, that's all we do. Yes, we did this in seconds. Imagine having to do this 1x to the 4 using the limit definition, having to FOIL that x plus h to the 4 power. That would have taken forever, right? Luckily we have these numbers. So the derivative of negative 9x, well, so what's the derivative of x itself? Isn't that just 1 times negative 9? That's just negative 9. Letter number 3, h of x equals to 1 over 5x. Or, well, in this case, we cannot use the general power rule to differentiate this function while the variable is in the denominator. So we need to rewrite this like 1/5 x to the negative 2. And, well, all we do is multiply. Instead of leaving these numbers indicated like I did before, I'm just going to go and multiply negative 2 times a fifth. That's a negative 2/5. And x to the negative 2, subtract 1 to negative 2, we should get negative 3. And we're done with the calculus. But for this type of questions, we don't want to leave them using negative exponents. You might want to go and write this in terms of positive exponents. So 3 brief examples here. All right. Well, let's see what's next. Well, another rule for differentiation is when we have the derivative of a sum of functions and the derivative of a difference of functions. So up to this point, what we have done is differentiate like individual terms. But of course, we are set to differentiate sums and difference, products, which will be the next section. So all we do is simply find the derivative of every single term. Right? That's pretty much what it is. Well, f prime of x. Let's find the derivative of 5x cubed. What's the derivative of 5x cubed? 15. 3 times 5, 15x, and subtract 1 to the exponent. That's 2. What's the derivative of negative 7? Just a 0. No need to write that 0, and that's it. For letter B, well, the derivative of 24x, the derivative of the square root of x, and the derivative of 5 over x. So we cannot just differentiate these two while they are in this form. So number 1, the radical function needs to be rewritten as x to the 1/2 in rational exponent format. And then this 5 over x needs to be rewritten with negative exponent, and only then we should be able to use the general power rule. So let's differentiate 24x. What's the derivative of 24x? 24. What's the derivative of x to the negative 1, of x to the 1/2? So minus 1/2 x to the, what's 1/2 minus 1? Negative 1/2. And negative 1 times 5, isn't that going to be negative 5? X to the what power? Negative 2, negative second power. Alright, so we're done with the calculus. Let's just reduce or write it in a nicer form. And actually what WebAssign will be asking you for, no negative exponents and no rational exponents. Write everything in terms of radicals. So that's 24 minus 1 over 2 x to the 1/2 minus 5 over x squared. And furthermore, 24 minus 1 over 2 square root of x minus 5 over x squared. And then that's just our final answer. Pretty simple, you know, better than doing the limit definition for this. Imagine having to do this madness with the limit definition. Well, actually we did one individually. We did a rational one, we did a radical one, but now we're not going to do this anymore. So, but again, on the exam, when you get tested on exam 2 on this topic, you will be asked to do one limit, at least one exercise using the limit definition. Could be a quadratic, could be a radical rule, who knows. And of course, I mean, by then you will know the differentiation rule. You could use your differentiation rules to verify the work for the limit process, but that's not going to be the work that you will be looking for. Okay, the derivative of the natural exponential function, the derivative of e to the x is itself e to the x, so it doesn't change. So let's do a couple of exercises in which we incorporate the e to the x. And in 1 second. Oh, actually, I was supposed to to eliminate, to scrap a through c right here. So we don't do those here. We don't do those today. So I'm gonna do letter D. Okay, so g prime of t. So what's the derivative of e to the t? Well, the derivative of the exponential is simply itself, e to the t. Now, what is the derivative of t to the e in this case? So we're essentially differentiating a power function, is some variable to a power. All right, so what will be the derivative of t to the e? Yes.
E to the power of t minus 1.
Yes, that's a general power rule. I mean, it's in this case, this power is not an integer like 5 to be 5 to the 4th power, right? So it's an irrational number. Let's just leave it like this. Oh, we cannot differentiate this this radical, so this should be plus t to the 1/3, right? T to the 1/3, and well, 1/3 t to the 1/3 minus 1. What's 1/3 minus 1? Negative 2/3. Well, let's write this in a nicer form. So that's e to the t plus e t to the e minus 1. That's plus 1 over 3 t to the 2/3. And then furthermore, yes?
Is it t to the negative 1/3?
T to the negative, yeah, negative 1/3, my bad, thank you. So negative 1/3 minus 1, isn't that going to be negative 4/3? Thank you. That becomes then 4/3. And going back to radical, that's e to the t plus e t to the e minus 1 and plus 1 over 3 cube root of t to the 4th. Coming back to radicals. Alright, let's move on. Well, you know what? Let me do one of this. So, let me do letter C. So in this case, what do we have here? Essentially, we have the quotient of the function. Well, later today, hopefully we get the chance to go all the way to the quotient rule. However, up to this point, we don't know what the quotient rule is, but we will. In this case, however, what we have to do is simplify the function, do the indicated operation, that is x squared over x, which reduces to x, 3x over x, that's just 3, and negative 7 over x, but I would like to write the x to the negative 1 so we can differentiate it. Alright? Well, so the derivative of the function, what's the derivative of x? 1. What's the derivative of 3? 0. What's the derivative of negative 7 to the negative 1? So multiply the power with the coefficient. Negative 1 times negative 7, that's a plus 7. X to the negative 1 minus 1, which is negative 2. But we don't want to leave this in terms of negative exponents, so we want to write them down, to write this x to the negative 2 as a positive exponent. That's 1 plus 7 over x squared. And that's final answer. So in some cases we need to do some algebra first before being able to differentiate. Well, let me briefly talk about letter B. For this one, we have a product of two functions. We're going to learn about the product rule in the next section. In the meantime, since we don't know the product rule yet, we would have to FOIL. Foiling, that's x times 2x, that's 2x squared. X times 5, that's 5x. And 3 times 2x, that's a 6x. And 3 times 5, that's a 15. Combining like terms, 2x squared plus 11. 11x, plus 15. And well, let's just take the derivative of this polynomial. So f prime, the derivative of 2x squared, multiply the exponent with the coefficient for x to the 2 minus 1, which is just 1. We don't need to write that invisible 1. The derivative of 11x, that's just 11, and the derivative of a constant is zeros, and that's going to do it for us. Alright? So again, in some cases we need to do some algebra first, some simplification first, before using the general power rule or whatever rule. Question?
Sorry, can you go back to D? I was wondering what you did to the ET. That.
This one?
So I see what happened to the TE, e to the E and the plus 1 over the CD. But for ET, is that just like say the same?
The e to the t? Yes, because the derivative of e to the x is itself e to the x. It's the same thing. Well, it's going to change when we have a composition function. When we'll go over the chain rule, that's going to look more interesting. So you'll see when we get to those rules. Higher order derivatives. Well, so in this case we can find a derivative, and then we can find the second derivative, and then the third derivative, etc., etc. What's the notation? Well, if we use the prime notation, so we go from f of x, let me just write f, to f prime, that's the first derivative, and then the second derivative, f double prime, f triple prime, and then for derivatives of order higher than 3, we don't write 4 primes. What we do is f parentheses 4 to indicate this is the 4th derivative, and so on for the nth derivative. Alright, so for the first 3 derivatives we use the prime symbol, the quotation mark, but not for higher than 3. If we use the other notation, well, dy dx, the second derivative would look like d squared y over dx squared. That's the second derivative. Third derivative, fourth derivative. So the order of the derivative, we write it as an exponent in the numerator on top of the d, and in the denominator on top of the independent variable, which in this case is x. Alright? So let's have a look at one example. Find the third derivative of y equals x to the 4 minus 6x squared plus 4. So y prime, that's the first derivative. So the derivative of x to the 4th will be, so first have the coefficient jump in the front for x to the power minus 1. So 4 minus 1, that's 3. The derivative of negative 6x to the second power, 2 times negative 6, that's negative 12. X to the 2 minus 1, which is 1. We don't need to write that one. So that's the first derivative. The second derivative, y double prime. So 3 times 4, which is 12, x to the 1 minus on the exponent, that's 2, minus the derivative of negative 12x, which is negative 12. So we're done with the second derivative. The third derivative will be, just keep using the same rules. 12 times 2, that's 24x, and the derivative of negative 12, what's that? 0. So we're done. Now, just jumping a little bit ahead of the game, as applications. So the original function, the given function, represents in physics a position function. The derivative represents the velocity function. And the second derivative represents the acceleration. Because we're going to have like a particle. So a function f of x describes the path, the motion of a particle along that given function. And well, the position function is that given function. The derivative is going to give us the position of the particle at a given value of x, at a given point. And the second derivative will give us the acceleration of that particle at that point. All right. So this concludes this section, I think. Yes. So let's move on to the next section, and that's the product rule and the quotient rules. Okay. So what if we have this product of the functions? Let's consider the function h of x equals x squared times x to the fifth. Well, the question is, can we just, find h prime of x by differentiating x squared times the derivative of x to the fifth? Well, if we differentiate x squared, isn't that a 2x? And if we differentiate x to the fifth power, that's 5x to the fourth. Simplifying this, that's going to be 10x to the fifth. All right? So it looks natural that, well, like in the previous example, when we found the derivative of a sum or a difference of the functions, we differentiate every single term of the function. Well, it should be natural that we just find the derivative of a product of a function by differentiating as a product this way. However, that's one way to think about. However, if we go back to h of x, x squared times x to the fifth, if we use some algebra first, that's an x squared, x to the second power plus 5. Using laws of exponent, that's x to the 7. So if we take the derivative of this function, h prime, that's going to be 7x to the 6th. But wait a minute. Compare the results. Are these the same results? These are not the same results, right? So one of these two procedures I did here has to be wrong. Which one is it? Well, we'll find out. Well, if some of you might have taken calculus in high school, or you took this class before, you know the issue here. So we are going to derive a formula for the product rule using the limit definition. This is most likely the last time we're going to do this derivation. Guys, I have a question here. I'm getting distracted, and you're distracting the people next to you. If you have an issue, please you have something to talk about, please take it outside or keep it quiet. Thank you. Okay. So, using the limit definition for the product. So we have a product of the functions f and g. If we were to set the derivative using the limit definition, we would have to replace every instance of x with x plus h and subtract the original function and then divide by h. So that'll be the setup for finding a formula for the product rule. However, well, what will be the next move? What will be the next step? Well, as in every single limit problem, so we would need to find a way to factor something out, to rationalize a denominator or a numerator, or to simplify, a complex fraction, or to expand a binomial or trinomial, etc. But I mean, looking at this expression, there doesn't seem anything we can do about it, right? However, we're gonna do a trick. And yes, well, this trick is just a giveaway. It's not something that you would be expected to know, nor you would be expected to derive this formula on the exam. It's something that I think it's worth doing. So, trick. So, subtract and add the quantity f of x plus h times g of x. Okay, so we're going to do this in the limit expression here. So let's go back to the limit, and I'm going to go like a limit as h approaches 0, that's f of x plus h, g of x plus h, and then we're going to subtract this quantity minus f of x plus h, g of x, and add it. So why can we do this? Well, that's because whenever we add a quantity and subtract it, it's basically adding 0, and that doesn't change the value of the expression. In other words, we're adding a special version of 0 in this case. But how do we do that special version of 0? Well, one that is convenient for our purpose. So another version of 0 is to subtract 5 and add 5. We still get the same result. Or to subtract x and add x, that's the same result as well. But in this case, well, the trick is to subtract f of x h g of x and add f of x plus h g of x, the whole thing over h. This is limit as h approaches 0. And well, what are we going to do? So we will factor any GCF that we see in each group of terms in the way that we group this. And well, number one, do you see the GCF? Any GCFs here? What do they have in common? The x only.
The x plus h.
The x plus h, but which one? Because we have a g of x plus h and f of x plus h. Which one would be? The f of x plus h. So we will have f of x plus h times g of x plus h
Minus g of x.
minus g of x. And then plus, do we see any GCF in the second group?
G of x.
G of x. So that's g of x times f of x plus h minus f of x.
So on the exam, are they just going to be the variables like this and not natural?
No, I'm just deriving a formula, so you won't be expected to do something this crazy. I'm doing this derivation because I think it's a good connection between the limit definition and then what we're going to do next. All right, so I'm going to split this into essentially two products of limits. This limit. So this will be, let me go all the way here, limit of f of x plus h as h approaches 0 times limit of g of x plus h minus g of x the whole thing I'm gonna divide by h. I don't divide this f of x plus h by h because this factor only corresponds to either one. In this case, I'm choosing to divide the second factor. Now plus limit g of x times limit f of x plus h minus f of x over h. As h approaches 0, h approaches 0. Well, did you notice anything interesting? So if we compute the limit, okay, what happens at h equals to 0? Well, h is going to go to 0, and well, this is simply f of x times, do we recognize this form? G of x plus h minus g of x over h. Isn't that the definition of a limit? But in this case, for the derivative of a function g of x, that's g prime of x. Plus, well, this factor right here, limit of g of x as h approaches 0. Well, there's no h to plug it in, so just write down g of x. And well, I think this one is easier to recognize. F of x plus h minus f of x. Isn't it the limit definition for the derivative of f? F prime. And this is the formula we want to use to differentiate a product of the function. And the definition is right here, it's right below in the definition box. Alright? Whenever we differentiate product of the functions, so we take the derivative of f, we multiply by the g of f, by the g of x, plus the first function times the derivative of the second function. A more compact way to write this is the derivative of f prime g, of f times g, that's f prime g plus g prime f. In other words, the derivative of the first factor times the second without doing anything, plus the derivative of the second factor times the first factor. And well, we're going to see this formula in action, so no more limit definition. The limit definition was just to make a connection between the original definitions of the derivative using limits and to come up with new rules. Alright, so when we're learning how to use a product rule for derivatives, it's important to, number one, identify our parts. So this first factor will be our u, and this will be our v. So how about, let's write them on the side. U, or actually not u, it's f and g. We will use u and v later. F and g. So f equals x squared plus 3x, and g equals e to the x. So let's take the derivative of each, because we need the derivative of both to put it together into the product rule. So what's f prime? What's the derivative of x squared minus 3? X. 2x plus 3. What's the derivative of g? What's the derivative of e to the x? E to the x itself. Alright, we have everything we need to use the product rule. Alright? So, y prime, which in this case we're going to use the product rule. Let me write down that product rule formula. So that's going to be f prime times g plus g prime times f. All we do is just write down these parts. F prime, which is 2x plus 3, times g itself without doing anything, not differentiating anything, e to the x, plus g prime, the derivative of e to the x, which is itself, e to the x, times f, which is x squared plus 3x. And well, that's how we use the product rule. That's the product rule in action. Well, you might want to simplify this. Well, factor out the e to the x. I want to factor the e to the x, and this will be e to the x times 2x plus 3 and x squared plus 3x. And if appropriate, combine like terms. In fact, we happen to have a couple of like terms, right? That's going to be 5x. So this will be e to the x squared plus 5x plus 3. So that's one problem using the product rule. How about we go back to the original problem we did for the product rule? So, but number one, questions about the product rule before going back to that question?
Yeah, could you explain again why g prime, the derivative, stays e to the x again?
Unfortunately, in this class, in Calculus 1, we don't have the tools so far we don't have the tools to explain why we will need the L'Hopital's rule and some other mathematical tools that we're going to learn later in the semester. And so let's just, in this case, we will just go with that the derivative of e to the x is just e to the 2x. E to the x. Okay. Right? Later, when we get to the L'Hopital's rule, I'll go back to that. Question?
Earlier for the product rule question.
Yes.
Just leave our answers like without distributing like the EX.
No, we need to. In this case, it's pretty simple to put together and simplify it. Especially in situations in which we are going to plug in to evaluate the derivatives, it's better to simplify them and then plug in whatever those values.
What different like the exam, like they ask you just for the derivative or without the leave our answer like that? The one call.
Well, that's just a setup. So that's the end of the calculus. And now we need to simplify this because if you input this on WebAssign, it might tell you that although your answer is correct, it's not written in the simplified form. So I would go with simplifying as much as we can. All right. So okay, let's go back to the same problem from before. So we had h of x equals to, it wasn't here, it was here, right? So how about we use the product rule with h of x equals x squared times x to the fifth. And in fact, if you guys see anything like this, don't overkill yourself, guys. Just use the algebra and simplify. However, let's verify the result using the product rule to find out why this is incorrect. So if f equals to x squared, g equals to x to the fifth, that means f prime equals 2x and g prime equals 5x to the fourth. So we have all the elements to write down to actually use the product rule. So h prime, which is f prime g plus g prime f. So f prime, which is 2x, times g, which is x to the fifth, plus g prime, which is 5x to the fourth, times f, which is x squared. Simplify each term. That's going to be 2x to the x to the fourth times x to the fifth. Isn't that x to the sixth? Plus 5 x to the fourth times x to the second. Same base. We add the exponent. 4 plus 2 x to the sixth. But well, we have like terms. 2 plus 5 7x to the sixth. Doesn't that match this result? And in fact, this proves that this is wrong. Alright? The moral here is the derivative of a product of two functions is not the product of the derivative, in the same way that we did in the previous section, that the derivative of a sum is the sum of the derivatives, or the derivative of a difference is the difference of the derivatives. The rules work for sum and difference, but not for product. And it won't work either for the difference. For that one, we will have a more elaborate formula. Well, some of you might already know that formula. Okay, I think I have another example using the product rule. All right, h of t equals t squared e to the t. So how about we make a list of our f and g e to the t. Let's take the derivative of f. That's f prime That's 2t. And the derivative of g, the derivative of e to the t is simply e to the t. All right? Let's put this together. H prime of t equals, well, using the formula, let's write down the formula. That's f prime g plus g prime f. So what do we have? F prime, which is 2t, g, which is e to the t, plus g prime, which is simply e to the t, f, which is t squared. Let's simplify this by just factor out the e to the t. E to the t times, how about t squared plus 2t. And there's really nothing else to do because these are two unlike terms and we're good to go with this one, right? So after a while, so I mean again, since we are getting to see this for the first time, well, I'm writing down this, I'm spelling this out like f and g, f prime and g prime.
Why'd you multiply by t squared?
Which one? Give me 1 second. That's g prime. Which one?
Before the final product.
This one? Because this is f prime g plus g prime f. Question?
For the final answer, can we also factor t as
We can also factor t, why not? We can also factor t, and that's t e to the t. What was that? T plus 2. That's another alternative. And actually this is good. This is a better form. Well, this will be a better form later when we get to finding maximums and minimums values for functions, because we will need to factor this derivative as much as possible so we can find those critical values. If you don't know what I'm talking about, you will later in the semester. In the meantime, let's keep practicing this product rule. Again, I'm going to write the whole thing, what f is and what g is and their corresponding derivatives. So f equals to e to the w plus 5w cubed, and g equals to w squared. All right? So the derivative of f is, what's the derivative of e to the u? It's the same, e to the u, and the derivative of 5w to the third, multiply the power with the coefficient 15.
Wait, why does it become, oh, g subtract 5 minus 3?
You subtract 1 to the exponent. G prime to e to, 2w to the 2 minus 1, which is 1. We don't need to write that one. Again, at the beginning, I will be writing all this for you. Later in the semester, as you get used to these rules, you won't have to write all this. It will just become a second nature, you know, like, oh, this is the first factor, that's the second factor. You can pretty much do this in your head. And of course, later in the next couple of weeks, we will be combining these product rules and quotient rules with derivatives of other functions, such as the trigonometric functions, the inverse trigonometric functions, logarithmic functions. We will put a lot together. All right, so let's write down the derivative. That's f prime. So again, let me go with the formula again. F prime g plus g prime f. So the derivative of f, which is e to the w plus 15w squared, times g, which is w squared. All right?
2w
Plus 2w, which is g prime,
minus dw.
Times, it's times f, which is e to the w plus 5w cubed. All right. Yes, let's simplify this one. So, okay, so number one, yes. So this will be e to the w, so that's w squared e to the w when we distribute here. And then when we distribute those, this is 15 w to the fourth and 2w e to the w, 2w, 5 w to the third, and this will become 2w e to the w, and 2 times 5, that's a 10, w times w cubed, which is w to the fourth power. Can we simplify this further?
Yeah.
Yes. So let me go with w squared e to the w plus 2w e to the w, and what is 15w to the 4th plus 10w to the 4th? 25 w to the 4th.
Can we factor out W more or no?
We can actually, yep, we can factor.
So on the exams, we just leave it like that when we get more.
That's fine. This is fine on the exam. But later in chapter, I believe it's chapter 4 or chapter 4, we would need to keep going with the factoring. That's w e to the w plus 2 e to the w plus 25 w cubed. That's another alternative either way. But this one is fine in this case. Yeah, I know sometimes it's crazy how in some cases it's okay to factor all the way, and in this case it's good enough if we have it this way. That's fine. Okay, let's go about one more question. You know what?